So welcome. It's Monday, October 12th, and thank you all for being here. Got a big class today. Huge. Packed today. So I mentioned on the very first day when I was introducing myself that I got my start doing clinical psychology. So I got my start with counseling. And this week I want to talk to you about relationships, because relationships are important. But long ago I gave up on doing like premarital and marital counseling. So now I want to talk to you about relationships between variables, because that's the kind of thing that I really enjoy now. Variable relationships are what we call correlations. So a correlation, you can see in the word, is relationship. So it's all about the relation between variables. In fact, the definition, correlation is a way of measuring the extent to which two variables are related. So what do we mean by related? Well, related when we're talking about variables is that as one variable changes, the other variable also changes. Now, as I'm saying that, it's almost like I'm saying that one variable causes the other to change, which is not actually what correlation is about. There's not a causal link between two variables, one changing causing the other to change, but there is some kind of relationship such that as one goes up, the other one might also increase, or it might decrease. That's the relationship. So we want to be careful as we talk about correlation to not assume that there is a causal link. It is true that if there is a causal link, that one variable causing the other to change will result in a relationship, but we can't argue back the other way, saying because one is changing along with the other that one is causing the other to change. So again, what do I mean by relationships? Well, unlike relationships with people, which can be complex and varied, understanding relationships between variables is pretty straightforward. So we're talking about variables that are scale level. They exist on a scale, and when you have something on a scale, the scale could either increase, or it could decrease, or it could stay the same. So when we think about two variables, when one variable increases, what do we see in the other variable? It's either going to increase, or it's going to decrease, or it's going to stay the same. And what we find in the patterns of how those changes occur is mathematically what we're defining as a correlation. So for example, let's take the scale for temperature. We know how that works, right? You have a thermometer. If it's really cold, the scale goes down. If it's really hot, the scale goes up. Well, as the scale goes up, if we are running the concession stand at the football game, what would we expect to find in the sales of cold soda as the temperature increases? When it's really hot, we're going to sell a lot more of the cold soda. But as we get further into the season and the temperature drops and it's getting down to the 40s, now what's going to happen to the sale of cold soda? It will decrease. So we're going to see a relationship where one goes up, the other goes up, one goes down, the other goes down. Those are moving together, or a direct relationship. Same idea, temperature. What's going to happen to the sale of hot chocolate during times when it's very warm? So if it's 80 degrees outside, we're not going to sell much hot chocolate at all. But when it gets down to the 40s and the air is crisp, oh, some hot chocolate sure is nice to warm up. So as temperature drops, hot chocolate sales will increase, and as temperature increases, hot chocolate sales will decrease. They move opposite of each other. Those are an inverse relationship. What will happen as the temperature changes to our sales of those foam #1 fingers that the fans like to wave in the stands? Is there going to be any relationship between temperature and foam #1 finger sales? Probably not. Now, those sales for the foam fingers might go up or go down depending on whether the team is winning or losing, but it won't relate to temperature. So in this case, there's not really a relationship. We might say they're unrelated or uncorrelated. The math behind this correlation is called the correlational coefficient, which we will summarize as R sub x, y, where x is one variable and y is the other variable. So the R is the correlation between x and y. This is called Pearson's R, and it's measuring how closely the data fit to a straight line. It was invented by Sir Francis Galton and perfected by Carl Pearson. And that R is the covariance of x and y divided by the variance of x and y separately. Before I move on, let me mention that R has a meaning, and it stands for regression, and something we'll call a regression line. So this week, the chapter is all about simple regression, but I thought it was important that we start with some examples about correlation, because correlation is fundamental to what we're going to learn next when we talk about simple regression. So I mentioned that it's the covariance of x and y divided by the variance of x and y separately. So variance, remember variance and standard deviation, variability, that has to do with the degree to which a variable deviates from its mean. What is the spread around the mean for this particular variable? Covariance is the degree to which two variables deviate from their respective means. And if we standardize that, if we convert it to z-scores essentially, if we divide by the standard deviations, then that becomes a correlation. So correlation is a standardized covariance. I also mentioned that correlation has to do with how well the data fit a straight line. And I said that R equals regression. So let's put that together. You see here a scatter plot, and running right through the middle of all of those dots is a straight line. That line is called a regression line, and the fact that the dots sort of line up around that line indicates that these two variables share something in common. They are variables, so they vary, but they also vary together, or they co-vary. That's what I mean by covariance. And again, if we standardize that, it becomes a correlation. So it's really how two variables vary together, and then we just do a little math to make sure that we can compare those variances, or covariances. That picture is a scatter plot. It's all those dots with the line running through it. So a scatter plot is the graph that we use to display correlational data. It's depicted with all these dots, which we call data points. So anytime we have a pair of x and y scores, that's a data point. If we take your height and your weight, those are two data points about you. We'll call one x, one y. They have some kind of relationship. Typically, as people grow taller, they weigh more. Now, obviously, if we take a dozen people who are all 5'10", they're not all going to weigh the same. So there's going to be some variance in height, there's going to be some variance in weight, and then there's going to be a certain amount of that variance that is shared. That's the covariance. A relationship exists when there's a particular y value that's paired with just one x value. So ideally, we would have, if all of our dots fit on a straight line, everyone who was 5'10" would weigh exactly the same amount. They weigh exactly the same number of pounds. But we know that isn't the case. However, if I gave you two different weights, someone who weighs 150 pounds and someone who weighs 90 pounds, and I ask you which one of them do you think is 5'10", you'd probably be able to make a pretty good guess, because 5'10" is associated with a range of values that's more likely to include that 150 than it would be to include the 90. And when we put all of those dots on a plot, put a straight line through them, that's called a regression line. That's how we visualize the relationship. What we will then do is work some math, or in fact, we'll let the software work the math for us, and it will give us a single number, which is called a correlation coefficient. Now this indicates the linear relatedness between variables x and y. It's going to be presented as a two-digit number. And it's going to be bounded by a positive 1 and a negative 1. So our correlational coefficient will never exceed positive or negative 1. And it will have a sign which indicates the direction of the relationship, and that will be either positive or negative. This is how you would see a correlational coefficient written. The R, which by the way is in parentheses, the R is in italics. The R equals regression, but it's the sign that we're doing a Pearson correlation. It's also called Pearson R. Okay, so when we see R equals, we know we're talking about a correlation. The positive or negative sign tells us the direction of the linear relationship. If it is a positive, those two vary together. As one goes up, the other goes up. The other one goes down, the other goes down. They are positively related. If it's a negative sign, then one goes up, the other goes down, and vice versa. You're moving opposite of one another. So the sign indicates the direction of the linear relationship. And then the absolute value of that number indicates the strength of the relationship. Close to 0, very weak relationship. Close to either 1 or -1, that indicates a strong relationship. So if we have like a negative 0.9 and we're comparing it to a positive 0.6, the negative 0.9 is a stronger relationship, even though it's a negative, than the positive 0.6. It's the absolute value of that number that tells us the strength of the relationship. So a positive relationship means that both move in the same direction. For example, as you grow taller, you tend to weigh more. The x value of height correlates fairly well with the y value of weight. A negative relationship, also called an inverse relationship, is when the variables move in opposite directions. So this would be that example with the football game temperatures and how much hot chocolate we sell. As temperature is high, hot chocolate sales are low. It's an inverse relationship. As temperature drops, it gets cold, hot chocolate sales increase. They're moving opposite of one another. And the strength of the correlation is how close it is to either 1 or -1. Values around 0 are weak. Values around 1 and -1 are stronger. If the relationship is perfect, those dots would all be on a straight line. So here I'm depicting a perfect negative correlation. When we look at the scatter plot, we also see a visual representation of the strength of the relationship, such that if the dots are close to the line, that tells us it's a stronger relationship. If they're on the line, the relationship will be perfect. If they're close to the line, it's strong. And as they get further from the line, they vary more, well, then the relationship weakens. Until eventually, if there is no relationship between the variables, we just have a elliptical cloud of dots where no particular x value predicts any y value. You might as well just guess with the mean. Well, that is actually the foundation for regression, which we're going to talk about next week. So if you have two variables that are related, we could predict with the mean, which would be our best guess with no other information, but we add a second variable, and now we can make a better prediction. We're going to focus on that in our next lecture. So as variability increases, the differences of the y-scores at each x become larger. So what we can do then is we can take that r value and we can square it. Now remember, anytime you square a number, it becomes positive. So a positive number squared is positive, clearly. But a negative number squared becomes positive. The r squared is called a coefficient of determination. This is our effect size. And it tells us something very specific. It tells us how much of the variability in one variable is explained by variability in the other variable. So remember, we started with covariance. These variables vary together. So how much of the variability in that second variable can be explained by variability in the first variable? That we get from the r squared. Now this is also going to be foundational to regression, because we're going to use r squared values, and we're going to use what are called beta values, B values to make predictions about a particular outcome based upon what we know about the relationship between X and Y. In fact, multiple X values and Y. Square the R value, we get the coefficient of determination, and we would interpret it like this. I have squared the R value, and I get R squared is a 0.463. I interpret that as 46.3%. So simply move the decimal 2 to the right. 46.3% of variability in doctor visits is explained by variability in apple consumption. So you can read between the lines to my hypothesis that an apple a day keeps the doctor away. I'm explaining almost half of the variability in doctor visits based upon apple consumption. Wouldn't it be great if that was true? Here's how this might look in a different example, a more real-world example, in fact, one that we may encounter relatively soon as we look at regression. If I have an effect size for burnout, in this example, an R squared of 0.42, indicates that a large portion of the variability in job satisfaction, 42% of the variability in job satisfaction, was accounted for by level of burnout. If I know how burned out you are on my scale, I can predict about 42% of the variability in your job satisfaction score. If I have more than one X value, I might be able to predict 60% or 70% of your variability in your job satisfaction score. So again, R squared is the amount of variability in one variable explained by the other. Well, that leaves some unexplained variability, which we depict as 1 minus R squared, called the coefficient of alienation. This is the proportion of variance in the Y variable that is unexplained by variance in the X variable. So in this case, our R squared of 0.463, 1 minus 0.463 is 0.537. We can also turn that into a percentage. Move the decimal 2 to the right. 53.7% of variability in doctor visits is explained by other variables, like how much you exercise and look after your weight and wear a mask, and things that you have control over. That explains the other half of the variability in whether you have to go see the doctor. So we have explained variance and unexplained variance, and our goal, our desire, is that we are able to explain as much variability in that second variable, or we'll call it the outcome variable, as we possibly can with all of our input variables. Going back to our example with burnout and job satisfaction, I might say 58% of the variability in job satisfaction was explained by factors other than the level of burnout. Factors like low pay, well, that would decrease your job satisfaction, or excessive paperwork, or inadequate health insurance. All of those things could decrease your job satisfaction, but they're not related to burnout. If I have information on your pay and your paperwork and your health insurance, I might be able to use all of those factors then to predict your job satisfaction. More variables, it's called multiple regression. So our plan for the next few lectures will be, we're talking about correlation this week, then we're going to do simple regression, which is one predictor and one outcome, and then we'll do multiple regression, which is multiple predictors and one outcome, and then we'll do model building, which is an extension. I'm going to use hierarchical linear regression, where we add variables, or we can remove variables, or we can get to a model that gives us the most amount of predictability with the fewest number of inputs. So that's our general pattern, what we're going to be covering over the next few weeks. So one last idea that I think is important to discuss is correlation versus experimentation. When we do a proper experiment, let's say we have an experimental group and a control group, we have control over the variables. We might say that we manipulate the variables. So manipulate, the root word being to work with the hands. We are randomly selecting subjects. We are randomly assigning them to groups. Who gets the experiment, who gets the control. With an experimental design, you as the researcher manipulate the X variable, so whether they are in the control group or the experimental group, And then you measure what happens to the y variable. So if we're measuring a drug, does their blood pressure go down? If we're measuring an educational initiative, does their outcome in education improve? So we're controlling one thing and we're measuring something else. With a correlational design, we are simply observing variables as they occur without manipulating them. Here's a great example that really illustrates why we need correlational design. So let's say that we were going to do, we wanted to do some study, research, about caffeine. And we want to know, does caffeine cause jitters? We're going to give people caffeine, and then we're going to measure something about their heart rate, or how much shakiness they have in their hands, or some other outcome variable. Could we randomly select a group of people who volunteer to participate, randomly assign them into the caffeine group and the no caffeine group? So we have the caffeinated coffee and the decaf coffee group, and then measure them for something about their heart rate and their blood pressure and their shakiness. So could we do that? And would people have a problem with our doing that? No, that would be okay. Now make a slight twist to that. Does smoking cause cancer? Can we randomly select a group of people to be in our smoking study and randomly assign them to groups like, you're going to smoke a pack a day, and you're going to smoke half a pack a day, and you smoke none, and then we're going to see who gets cancer? Would there be any ethical problems with that? Of course. Yeah. So we could not do an experiment with does smoking cause cancer, at least not with human beings. Now, if you're a lab rat, then you're hosed, because they can do whatever they want, and they'll put you in the smoky-filled cage and see if you get lung cancer. But we don't do that with human beings. So if we were going to do a smoking causes cancer study, what we would have to do is find people who smoke and ask them, how much do you smoke? And if they say, I smoke a pack a day, well, you're in that group. And if they smoke half a pack a day, they're in that group. And if they're a non-smoker, they're in that group. And then we track them over time to see how many of them develop lung cancer. So in this case, we are observing the variables as they occur naturally. We're not manipulating. We're not selecting them to be in the pack a day group. They have self-selected to be in that group. Now this is where we go back to that correlation and causation idea. We cannot, just from that one study, conclude that smoking causes cancer. If that same study were repeated a lot of times, that same correlational design, and the observational study, and we pull records from the hospital and we find out of the people who are in the hospital for lung cancer, how many of them are smokers, and we find a dramatic difference between lung cancer between smokers and non-smokers, well, now there is a consensus that yes, smoking does cause lung cancer, but it doesn't come from a single correlational design. It would have to come from multiple experiments and multiple observations. So again, if there is a causal link, you will see a correlation, but we can't argue from a correlation, especially from a single correlation, that there is a causal link there. Well, that's all that I have to tell you about correlation for this week. Do you have any questions? Anybody? You over here? Yeah, nobody? All right. For the assignment, there is a 10 question / 20 point assignment for you to do this week. If you were here or watched this video, you have pretty much everything you need to know to answer all the questions on that assignment. But I've also given you some class notes that cover the same materials, what we covered today. So between those two and some extra videos, you have all of this information. Go ahead and get that knocked out. Of course, we also have test 2, which is due at the end of this week. So this is kind of a light week on study, on new material, and you can also use that additional time to work on your test. Okay. Well, if there's no other questions, then thanks for being here. I'll see you guys next week.